Okay, so how do we correct for multiple comparisons in the context of fMRI? Well, there's two main strategies. And the first one that we're going to see is to correct for the number of comparisons that we have. And this you can do in multiple ways. You could use a family-wise error correction. And see, when you adopt this approach, what you're trying to do is you're controlling for the probability of any false positives. So you're saying, over all the tests that I'm doing, over all the 100,000, 200,000 tests that I'm doing, I want to only have 5% probability of getting one false positive or more. And the type of strategies that use, the type of corrections that use this strategy are Bonferroni, cluster correction using random field theory. You can also use permutation, although we won't see it today. A different class of approaches is known as false discovery rate correction. And here, what you're doing is something slightly different. Rather than saying, over all of my tests, I want the probability of having one false positive or more to be at most 5%, what you're saying is, of all the voxels that I do declare active, I want to control the proportion of those that are false positives. So I'm saying, instead of saying, of all the tests that I'm doing, only 5%, I have only a 5% chance of getting a false positive. With FDR, you're saying, of the voxels that I find to be significant, at most 5% of those are false positives. Let's start with Bonferroni. You're probably familiar with the idea of Bonferroni. You might have encountered it and used it in other contexts outside of fMRI. And the main idea is to just make each individual test out of the 100 or 200,000 that you're doing, set the alpha of each individual test to just be much, much more stringent. So that once you do the 1 minus alpha to the n, or to the 100,000, that becomes 5%. So you want to set the test of each voxel to be so stringent that when you consider the whole family of 100,000 tests or 200,000 tests, altogether, those give you a 5% chance of one false positive or more. So the idea, it looks something like this. In order to achieve a family-wise Bonferroni's of 5%, let's say, a family-wise, so over my 100,000, over my n tests, I need to set each individual test to be 5% divided by n. So again, in our case, let's say we want a 5% family-wise error rate. So we want, over all the tests that we're doing, we want at most to have a 5% chance of having one false positive or more. Then let's assume we have a total number of, and I have to stress, independent tests. I'll get back to this, of 100,000 voxels. So the Bonferroni corrected false positive level for each individual test, so the Bonferroni corrected alpha for each individual voxel has to be 0.05 divided by 100,000, or this number right here. If I calculate 1 minus, open parentheses, 1 minus this number to the power of 100,000, it will give you exactly 5%. Okay, so again, with Bonferroni, you're just really cranking up the dial of how stringent the test has to be at each individual voxel, so that as a group, you have 5% chance of one false positive or more. Now, Bonferroni is great. However, it does have one very important assumption. It assumes that the tests, the 100,000 tests that you're doing, are independent. And so, for example, it assumes that the values look something like this, or maybe like this. Unfortunately, fMRI data, as you know well, are not independent, or rather, fMRI voxels are not independent of each other. fMRI voxels are spatially correlated, meaning the values of voxels nearby are dependent upon each other, are correlated. And that's because the brain is smooth in of itself. Vasculature plays a role. We smooth voxels during preprocessing. And of course, if you imagine a certain part of the brain responding to a task, it's very likely that that part of the brain spans more than just one voxel. So of course, you're going to get contiguous voxels that are not independent, because they have in them neurons from similar populations that respond to similar stimuli. So unfortunately, this hypothesis of independence is not tenable with fMRI data. And as a result, Bonferroni just becomes really overly stringent. And you're really, with 100,000 to 200,000 tests, you really have to crank up the dial of how stringent each test needs to be, so that all the tests together give you 5% chance of a false positive or more. And so you obviously expose yourself to a great risk of type 2 error, meaning there will probably be a large number of voxels that in truth are associated with your task, but because they're associated not as strong with your task, and we've cranked the dial up so much in terms of the correction, those voxels will appear non-significant. And finally, of course, it's just hard to find what N could be in fMRI data because they are smooth in order to even implement Bonferroni. So Bonferroni, I think very few people ever do Bonferroni today, but theoretically, it just doesn't stand. Now, a second way of approaching the problem is to use cluster correction based on random field theory. Now, the idea is that we can use random field theory, which is a relatively recent body of mathematics that defining theoretical results for smooth statistical maps. We can use random field theory in order to find threshold in cases where it's not really possible to find independent variables, and thus it's impossible to apply Bonferroni. This is just a different strategy to threshold fMRI data. Now, this is a three-step process, and if you look at the image on the bottom right, just to give you the intuition, we will then look into these three steps separately. But if you imagine this being a slice of brain, so X and Y are spatial coordinates. Z is the intensity of the statistic at each voxel. Now you can imagine this being data, and random field theory helps you find a threshold in these data so that you can expect to get only by 5%, only a 5% chance of getting in null data, so where there's no significant effect, a little peak above that threshold. So we use random field theory to calculate where would we have to threshold some null data in order to only have a 5% chance of getting a peak above that threshold. And then we apply that threshold to our data. Now, in order to do this, we need to follow three steps. First, we need to take our data and calculate how smooth they are. And we will do this by calculating something referred to as results. Then we will say, okay, so if I had data this smooth, and let's assume there's no effect in there, so it's H0, there's no significant effect in there, how high a threshold do I need so that in this smooth data that's just as smooth as your real data, so that I have only a 5% chance of getting one or more peaks above that threshold. And then you bring the threshold to your data and you threshold it with that. But let's take this one step at a time. First, the first step of this is to try to understand how smooth your data are. Now, as I said earlier, we can't compute the number of independent voxels in fMRI because voxels are not independent over space. What we can compute is the number of resolution elements, also known as results. And the reason we do this is not to find how many independent results there are, because that's not what results are. Results are not the number of independent things in the image. The reason we do this is because we need to understand how smooth your data are. Now, so a result is really defined as a clump of pixels of the same size as the width of the smoothness of your data. So a result is sort of is the size of the kernel of how smooth your data are. Now, if you're asking, well, okay, so how smooth are my data? How do you tell how smooth my data are? Think of it this way. Imagine taking a white noise image, just like the one I showed you at the very beginning from the simulation. Imagine taking just completely white noise image and smoothing it all the way until it matches the smoothing of your data. That's how you calculate it. You take just a simple white noise and you smooth it and you massage it until the smoothness of that is the same as the smoothness of your data. And then you can say, okay, so at this point, I know that I had to smooth these white noise data by, let's say, 5 millimeters by 3 millimeters by 7 millimeters in order to make them as smooth as your data. So now I know how smooth your data are. This is sort of the little sort of runaround logic in order to estimate how smooth your data are. But still, the key point is we calculate how many results there are in your image as a means of understanding how smooth your data are. To make this a little bit more sort of concrete, imagine that the result count is the number of voxels divided by how smooth your data are. So to make this, as I was saying, a little more concrete, imagine you had, and that's the image down here, imagine you have 10 voxels, the pink one, and imagine I were to tell you that I found out that your data, the smoothness of your data is 1.5. So if you do 10 voxels divided by the smoothness, it turns out that each result, that you have 4 results, and each result is 2.5 voxels. Okay, so now this is how smooth my data are. Remember, it doesn't mean that these 4 results are independent, but it gives me a measure of how smooth the data are. And it'll be apparent why I need to know how smooth the data are in the next step. Now, 2 important things to keep in mind, particularly if you're a user of fMRI. Because fMRI has a little tool called 3D Clust Sim, which will ask you for the smoothness of your data. FSL, on the other hand, will estimate the smoothness of your data from your data. Now, the kernel of the result, so the smoothness of your data, is not the same thing as the smoothness that you imposed with when you did blurring, when you did the spatial smoothing. And the reason is that the brain in of itself is already smooth for the reasons we said earlier. Think vasculature, think proximal neurons doing the same thing. So typically, the smoothness of your data is a little bit larger than the smoothness of the kernel that you used to smooth your data. So just don't get tricked into thinking that the smoothness of your data is the same thing as the kernel that you used to smooth your data during pre-processing. And finally, do notice that the number of results really only depends on how many voxels you have and how and what is the size of the smoothness of your data. So now that we know how smooth the data are, the next question is, well, how likely am I to get, if I had a null data set that were exactly this smooth, how likely am I to get big peaks of activation that would look like activations, even though there would be false positives? And so in order to do this, and so this is the second piece of the puzzle, we're going to use the Euler characteristic, typically referred to as chi, which is a topological feature of thresholded maps. And it goes more or less like this. Imagine you have some data just like this. The Euler, and then imagine thresholding it at, let's say, maybe at 0 right here. Imagine putting a plane right here and chopping it so that anything below it goes to 0 and anything above it goes to 1. Then if you looked from above, it would look something like this. Now, the Euler characteristic is the number of blobs, so the number of individual yellow blobs. For example, this is a blob, this is a blob. I think this whole giant thing is one blob. Here's another one, and there's one right there. The Euler characteristic is the number of the blobs minus the number of holes. Now, said this way, it doesn't really help much. However, what is interesting and what is really helpful about the Euler characteristic is that if you set the threshold high enough, the Euler characteristic just becomes the number of blobs. For example, if instead of thresholding at 0, this image right here, I threshold it a little higher, right? Now I really only get blobs. I don't get holes anymore, I only get blobs. And in fact, the higher you threshold it, and more the probability of getting each blob is really nothing but the expected value of the Euler characteristic. So in other words, I can use the Euler characteristic to estimate how likely am I to get a blob above a certain threshold just by chance. So we're using this property of the Euler characteristic in order to find in a smooth field that is just as smooth as my data, where should I threshold so that I at most have 5% chance of getting one blob or more above that threshold in null data. And so we can make this threshold even higher. And now I only get, let's say, these 4 blobs right here. And then we can make the threshold even higher. And now I get only 1 blob. And the expected value of the Euler characteristic at this threshold, whatever the threshold was that generated this, is the probability approximates the probability of getting at least 1 blob. So if we're using null data, the expected value of the Euler characteristic is really my alpha, my family-wise alpha. In other words, if there were no effect in my data, what this is saying is if there was nothing in my data, if my data were complete junk, what is the probability of getting a supra-threshold blob, something like this? In other words, a false positive. It's exactly the expected value of the Euler characteristic. Okay, so let me take a step back just to put it all together. So in the first step, we take our data and we estimate how smooth they are. So that then we can take a completely null data set, smooth it by that same amount, and we'll get something that looks like this little map of mountains and valleys. And then what this procedure does is it chops this map of mountains and valleys in order to find what is the probability of getting 1 or more blobs at each of these different thresholds. And then what you can do is you take the threshold that gives you whatever you want to be your family-wise alpha. For example, you might take the threshold that gives you 5% chance of getting a peak above that threshold when you're using null data. So under completely null data, if there's nothing happening in my data, I have at most 5% chance of getting 1 blob above that threshold or more. So now I can take that exact threshold and now I bring it to my data and now I'm going to threshold my data with it. So we use the Euler characteristic just as a tool because the probability of the expected value, of the Euler characteristic just so happens to be the probability, to approximate the probability of getting 1 blob or more above a certain threshold. And so step number 3 is where it comes all together. And this is actually the expression for deriving the threshold. But to put it in English, you can see it this way. Given how smooth my data are, the result count, right, which we calculated earlier, what threshold Z do I need? So how high up do I need to cut these data, to cut the map of data so that I get a family-wise alpha, which happens to be approximated by the expected value of the Euler characteristic, of having one peak or more above threshold. And see, the reason why we need to know how smooth your data are is because look at these two cases. If your data are very spiky, right, then you will probably tend to get a lot of small activations. Whereas if your data is very smooth, it's unlikely to get, right? If you get one big peak like this, it's unlikely to happen just by chance, right? So we want to know first, how smooth are your data? Second, given how smooth these data are, how high up do I need to put my threshold so that, as per the Euler characteristic, I have at most 5% chance of getting one blob or more above the threshold. Okay, so it's kind of this three-step procedure in order to find the correct threshold that I will then take and bring into my data.